Okay, let's get started. So hi everyone, my name is Yann. I'm a researcher at OpenAI, and I'll be re-recording a class that I gave at the Berkeley LLM Agents MOOC series on Introduction to Training LLMs for AI Agents. So the reason why I'm re-recording this class is because one, we had technical difficulties early on in the class, and second, there was a fire alarm that started, which means that we did not go through all the slides. And also we don't have a good recording, and I want to make sure that everyone who's online would also see the entire class. So before getting started, one thing to say is that all views here are my own. Even though I work at OpenAI, I will mostly talk about things that we can find online and information that we can find of open source models, especially Kimi, Llama, and DeepSeek. So unless I talk about OpenAI, nothing is related to OpenAI here. Great. So with that, let's get started. So we all know that LLMs and chatbots really took over the world in the last few years. So the question I will try to answer is, how do we actually train those? How do we train those models? So this is an example here from ChatGPT and an answer from ChatGPT. So there are three main parts of the training pipelines when training an LLM. The first one is pre-training. So you probably all heard about it. The general mental model that I like to give people is that pre-training is really about predicting the next word on the internet. So you take all of internet or all the clean part of internet and you just try to predict the next word. And as a result, you will learn everything about the internet and as much as possible about the world. In terms of data, pre-training takes more than, at least for the big models, the big open source models, takes more than 10 trillion tokens. So that's a lot. And when I say tokens, you can think a little bit about it as words or like subwords, but essentially more than 10 trillion tokens. So think about it as like 10,000 words. 10 trillion words. It takes months to train on that much data. And it takes a lot of money and a lot of compute to actually train on that amount of data. So you can think about the compute cost being more than like 10 million for one run. So here the bottleneck in pre-training is both the data, as we talked about, 10 trillion is a lot, and second is compute. And as we will see, basically the more you scale up these models, so that means the more data you put in the model and the more compute, so the more the longer you train for, the better the performance will be. So an example of a pre-trained model is like Llama 3, for example. So a second part, which actually is third in a chronological order of how these models are usually trained. But this is the second part that came after pre-training. The last part is more recent. So the second part is classic, what I call classic post-training or RLHF, so reinforcement learning from human feedback. Here the idea is that this pre-trained model is just good at predicting the next word, but it's not really good at performing well in the sense of predicting what the user wants, or predicting, or like answering questions, or like following instructions. It basically, you can think about it as a model that knows everything about the world, but it doesn't actually know how to interact with a human. That's one way of thinking about it. And that's what we're going to try to optimize for, is more this interaction with humans and making sure that when you ask it to do something, it does it. The data size here is much smaller, maybe around like 100,000 problems. All these numbers are just orders of magnitude. And just to give you a sense, in terms of time, it probably takes a few days to do a few days to do one of these runs. Compute cost maybe around like $100,000. And here the bottleneck is data and evals. So when I say data, I really mean the quality of data, because 100,000 problems is not that much. So it's really about high quality the data is, and whether you know whether you can evaluate whether you're making improvements on your run. So how good you're improving your run. And this is really important, because when you do this RLHF or this post-training, you have to balance many things together. So you need to make sure that you're actually tracking your performance on all these different axes. So a specific instantiation of this RLHF model is a Llama instruct. So when you hear instruct at the end of the model, that usually means that it just went through RLHF. Because it can now do instruction follows. It can follow instructions that are given by humans. Great. And this last part, which actually, as I said, usually comes second in the pipeline, is what I call the reasoning reinforcement learning. So the idea here is to think on questions where there's objective answers or where you have access to ground truth. So you will hear recently, you will hear from open source models also that like perform very well on math and like coding and things where it's actually pretty easy to get some ground truth answers. For example, like passing test functions in coding or like passing some math exam. And this is what you want to optimize during this reinforcement learning for reasoning. So this second stage is only true for reasoning models. So one example is DeepSeek R1, which was the first reasoning or the first open source reasoning model. In terms of data, so they don't in the R1 paper they don't say exactly, but you can kind of read through the lines. And you can look at the plot and try to extract around the amount of problems that they're actually training on. So in terms of data, it's probably around 1 million problems that they're training on. Probably takes in the order of weeks to train this second stage, so this reasoning stage, around $1 million. And here the bottleneck is reinforcement learning environment and hacks. So what I mean by that is, as I said, this is about optimizing for objective truth, or optimizing, for example, if you take the case of passing test functions in coding, the bottleneck is how many test functions can you get. And one thing that will usually happen is when you start optimizing for these test functions or test cases, you will see that the model will start optimizing things that you weren't expecting. So maybe it will be able to pass the test case by, for example, removing the test in your environment or replacing it with always returning true. That's like one of the type of thing that the model may do, which is what we usually call hacks. So the way to think about hacks is just the model found a way of optimizing the reward, even though that's not what you were hoping they would do. So this is usually a pretty big bottleneck because models are really good at optimizing things, even if it's not exactly the type of thing that we want to optimize. If you write something to optimize, they will optimize it exactly as written. And usually the second stage, the second and the third stage, I will bundle them together and call them post-training, which comes after pre-training. It kind of depends. Different people have different names. That's how I believe R1 and Kimi talked about that in the post-training stage. Great. So the LLM training pipeline, there are basically 5 things that you need to consider when training an LLM. First is the architecture. So what model architecture are you using? So you probably all heard about transformers or about mixture of experts, which is a kind of a variant of transformers. And then there's a training algorithm and the loss. So that means what are you optimizing for this architecture to do? So what are you trying to optimize? And then there's the data and the RL environment. So that's what we talked about before. This evaluation, which is knowing whether you're making any progress. And then the last part is systems and infra to make sure that you can scale up these runs. So until I would say 2023, most of academia was actually focused on architecture and training algorithm and losses. I've done also a PhD. That's what I was focused on until around 2023. And really, there were a few people who were working on the rest, but that was like the main, the main part of academic research. But in reality, what matters in practice is the last 3. So what matters is usually data, evaluation, and systems to be able to scale. So people usually want to work on architecture, on like developing new algorithm for optimizing your model. But these things matter much less, as we will see, than really how much data do you put in, what's the quality of your data, are you measuring your progress well, and do you have the infra to actually scale things up. So I will not be talking about architecture, mostly because at this point, the architecture is not changing that much in the open source. So it seems to be mostly using kind of transformers with a mixture of experts. And a lot of people like talking about architecture, so you can find a lot of information about what architecture is being used. And as I said, it's I think it's at least currently it's really not as important. So that's why I will not be talking about that. Okay, there's two last spots that I didn't talk about in the kind of pipeline for training LLMs, and that's I consider them more about specializing the LLM. One is prompting. So once you usually have a model, for example, a big lab or a big big lab might release a big open source model or a closed model, and then people will be able to interact with it and specialize it, that model for their use cases. And the usual way that people do it is first just by prompting. So prompting is really just knowing how to ask questions, essentially. So it's kind of the art of asking the model what you want. What is nice is that you don't need any data. And it's pretty fast. You just try a few examples and you see how it works. There's kind of no compute associated to it, or very little. And the bottleneck is eval. Like, how do you make sure that you actually have a good prompt, that you're asking the right question to the model? And then the second part is fine-tuning. So we will not be talking about it, but just to mention it here briefly, this is the fine-tuning is basically continual post-training or an addition of post-training, where you basically apply the second stage of post-training to domain-specific data. So for example, imagine that all these models actually release pretty general, all these companies release pretty general models, and now you want to specialize it to some specific domain, like medical data. So you might have, like internally, you might have, or for your project, you might have some specific data that you want to optimize for, and you will take these open source models and you will be basically fine-tuning. So doing a little bit more of training on your specific data. And just like post-training, this requires around like maybe 10,000 to 100,000 problems, around days, and like compute costs around like 10,000 to 100,000. And here again, just like post-training, the bottleneck is really the quality of your data and evaluation. How do you know whether you're making progress? Great. So let's talk about pre-training. I will talk about the method, what pre-training is, the data, and the compute that you need. So in terms of pre-training, the usual, as I said, the mental model that or like the metaphor that I like giving to people is that pre-training is about predicting the next word. And the way to think about it is just, for example, when you type a message, you will usually see your phone like predicting what's the next word that you will predict. And this is exactly how pre-training works. So, or not exactly, but like mostly this is kind of the metaphor that I like giving, and it's essentially how pre-training works. So the goal of pre-training is to teach the model everything in the world. And the way that we basically achieve that is just to predict the next word. Because if you can predict the next word, then you must understand. If you can predict the next word on every single domain, then you must have like some understanding of that domain. And that is basically what pre-training is. So in terms of data, it's basically any reasonable data on the internet as much as possible, because you really want to, again, you want to have models that understand as much as possible at everything. So you really want to give as much data as possible for the model to learn on. So in terms of scale of data, you have around, maybe I said more than 10 trillion tokens. So for Llama 4, for example, I believe the models were trained with between 20 to 40 trillion tokens. For DeepSeek V3, I believe it was 15 trillion tokens. So it gives you kind of an order of magnitude of data that you need for the current best open source models. So that 10 trillion tokens corresponds to approximately 20 billion unique web pages. So that's a lot of data. It's not all of internet, but it's basically all the clean data that people can find on internet. And pre-training has really been the key since GPT-2 in 2019 that mostly showed the world what pre-training can do, and basically just using a simple method like predicting the next word, but you just do it at scale. It really showed how smart the models can become. Okay, so what is actually happening under the hood? I'll give you first a brief overview. In terms of tasks, as I said, it's about predicting the next word. So the steps are the following. First, you tokenize the data. So here I have a sentence, she likely prefers, and the goal is to predict the next word. So in this case, the next word is dogs. So she likely prefers. So what you will do is you will split up she likely prefers into different tokens, which are basically different subwords or different subunits. The reason why we do that is because computers, I mean, they don't understand words. They only understand numbers. So you have to take these words, or you have to take this sentence and split it up into numbers. So that's what we call tokenize. So once you have, I split it up by word here, so by space. So I have she likely prefers, and I say all these three words become tokens. And I will associate all of these tokens with a different index. So she, I will give it 1, likely becomes 2, and prefers becomes 3. This is just one way of converting, again, these words that computers don't understand to like numbers that computers can work with. Then you will do what we call a forward pass, which means that you will pass it through the model. We'll see exactly what happens later, but you will pass it through the model. So usually this is a transformer. And then you will have this model try to predict a probability distribution, so a categorical distribution that tries to predict what is the probability of the next word. So for example, here you see that she likely prefers, it's very unlikely to say she again, but it's very likely to say this word, which in this case is dog. And then you will sample from this probability distribution. So once you have a model that predicts a distribution, you can just sample, and that's why every time you ask a question to some open source model, I will not always give the same answer because you actually have this sampling step. You sample, and then you detokenize, because again, when we talk about it in this categorical distribution, that just tells me that this is token number 5. Here I have 1, 2, 3, 4, 5. I have one index here. So I have 5, and then I need to look through my dictionary that tells me index 5 was actually the word dogs, or the token dogs. So that's a detokenize. So the last 2 steps, this is not super important, but the last 2 steps are only happening at inference time. At training time, all you can do is you can always keep predicting the next word by predicting the probability distribution and just optimizing your cross-entropy loss, which I'm sure most of you are familiar with. So you don't actually need to do the sampling. So these 2 steps are only during inference. Great. So now I want to give you some intuition about why this can even work. And to do that, I will talk about, honestly, kind of the most simple language model that you could think about. And this is the Ngram language model, which was already used at scale in 2003, so like a very long time ago. It already worked pretty well. But I think it gives a good intuition of what is happening under the hood for the current models. So the question here is, how can you learn what to predict? Because we talked about before, I said, oh, you just do a forward pass to your model and just predict a distribution. Like, how can you learn that? So one way you can do that, so let's take an example. Say, how can you know what comes after the sentence, the grass is? And you probably know that after the grass is, it's most likely to be like green, for example. So how can we know that? How can we teach the model to do that? Well, the solution is statistics. Statistics is always the solution to most of your problems. So one way you can do that is you can take all the occurrences of the sentence, the grass is, online. Or for example, take all the occurrences of the grass is on Wikipedia. And now you can predict the probability of every word that comes after the grass is by looking at the number of times that that word appeared after the grass is, normalized by the number of time that you saw the sentence, the grass is. So let's say that like the sentence the grass is happens 1,000 times on the web pages that you looked at, and maybe half of the time, so maybe 500 times, the next word is green, and maybe like, I don't know, 100 times the next word is red. You will have then probability of green knowing the grass after the grass is will be half, so 500 divided by 1,000, and for red it will be like 10%, so 0.1. So that's a very simple way of predicting the distribution, the categorical distribution of the next word. But this would work. It would actually work pretty well, at least for simple things like the grasses. That would actually work pretty well. There are still a few challenges. One is that you need to keep count of all the occurrences for each of these n-grams, or at least in this case, each of these sentences that happened. You need to keep count of every word that came after. So just think about it in terms of memory. It's a huge memory requirement for storing all of that. So that's unfeasibly large, but it will still like work pretty well for simple things. And then the other problem is that most sentences, maybe not most, but like a lot of sentences might be unique. So if there's something that never happened in your training corpus, so if you never saw this like very long text, let's say that instead of the grass is, I give you 100 lines of like code and I ask you what's the next word, maybe you never saw these 100 lines of code at training time, and then your predictor will have no way to generalize because basically count will be 0, so we'll give a probability of 0, even though the probability is actually a little bit higher than 0. That's like two problems that you would have with this very simple kind of statistical language model. So the solution is very simple. Just use neural network. So if you, I'm sure many of you know about neural networks, and we're going to assume that you do. But basically, you can just estimate, or at least approximate. You can basically approximate this prediction by using this parametric estimator that neural networks are, instead of this non-parametric estimators that we talked about here. Great. So let's go through what I will call here neural language models. So it's a language model of a neural network, which is what everyone does. So the way that this works, again, at a very high level, is that you take a sentence. For example, I saw a cat on a. I will basically split the sentence into different tokens. I will associate, so these are all these words. I will associate all these tokens with a word embedding, so like a vector representation of that word. So the way that you can think about it is that imagine that this was in 2D. You basically have a plane, and you basically have all these points that are on this plane, where usually like more similar words clustered with one another. So you might have like I saw a cat and things like this. It's just that instead of being 2D, it might be like much higher dimensional. It might be like a vector space of like 768 dimensional and stuff like this. Then you pass that to a neural network. So neural network, the way to think about it is just some non-linear aggregator of these vectors. So it's just something that takes all these vectors as input. It does some merging and gives you another vector. The important part is that it's differentiable. So the way that you do, so you can actually backpropagate through that. That's like the most important. But for example, you could use a very simple neural network. Could just be an average of this. You could literally just average all these tokens together, or the vectors associated with these tokens, and it gives you another token here, which is intuitively, it's the vector representation of all this sentence, I saw a cat on a. So again, you could take some average, or you could just take some like nonlinear aggregation, like passing through a neural network. Then what you do is that this vector representation is in the wrong dimension, because what you want to be able to predict the number of like which is the most likely word. So you want to predict like the probability of each word. So you want a representation that lives in this dimensional space. That is the number of dimension is the number of tokens, the number of words that exist in your language, for example, English. So what you will do, a very simple way, is that you can just pass this through a linear layer. So you can just multiply this by a matrix to take this H representation that lives in D dimension and pass it to your vocabulary size dimensions. So let's say very concretely, you have 768 dimension. Let's say that your vocabulary might be like 20,000 words that you might want to predict in English. And you will basically multiply this by a matrix of 768 by 20,000. And then you will get a vector out of it that is 20,000 dimensional. Great. So once you have this, you will just pass it through a softmax. So softmax is the usual trick to get a categorical distribution from any vector. So this just ensures that basically you have numbers that sum to 1 and are between 0 and 1. And then you can just consider that as the probability of the next word after I saw a cat on a. And here you basically have this prediction of the next word. Great. And once you have the next word, you can just optimize the cross entropy loss. So basically just try to optimize what the real word is. Let's say that the real word comes from here. You will basically try to maximize a little bit this one and minimize all the rest. And then you just backpropagate because everything is differentiable. And that will basically tune all the weights that you have in your neural network, including also these word embeddings. So this representation for every word. Okay, that was a very brief overview, but hopefully you get a sense of what a neural language model is. Okay, so now we talked about the method. Let's talk about the data that goes into pre-training. So the idea, as I said before, is to basically use all of the clean internet. So use as much data as possible and everything that is clean on the internet. Why do I say all of clean internet? Is because internet is actually the majority of internet is pretty kind of dirty and not representative of what you want to ship to users or what you want to optimize your model on. So a very practical type of pipeline. So every different like lab and different pre-training groups have different ways of doing it. But that's just to give you a broad overview. You first download all of internet. Usually people use in the open source some crawlers that already downloaded internet for them. So basically, for example, the common crawl is a crawler that already downloaded 250 billion pages. So that's around like more than 1 petabyte of data, and they're all in these WOC files. So basically, you download all of internet. The second thing and how these look like. So these files, it's basically just HTML. So you will see that's pretty. I mean, it's hard to understand. You see here some meta, some keywords, and here you will find the text that says blah 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 blah. Or here, paragraph. One of the best and most rewarding features of the blah blah. Or that. So it seems to be like an ad talking about rewarding features, and then it talks about downloading free question and answers. Anyways, it seems to be pretty kind of an ad. So anyways, this is a random website that I took from Common Crawl. So as you see, it's like kind of hard to parse, and probably this is not even something that you really want to train on if it's an ad. Great. So that's just an example of what you have. Oh, my computer stopped. Oh, like this. Great. Second thing that you do. So as you just saw, you have this HTML. So what you have to do is you have to extract text out of it. So it's actually pretty challenging. There will be some question of how do you deal like with JavaScript or like boilerplate code or like math that is run differently and things like this. So you will need to extract text from HTML. This is actually pretty computationally expensive because at this point you really have the name of the game is how much data you can have. So you really have a lot of data that you have to clean and extract from. So that's actually pretty computationally expensive. Then you will do some filtering. So one filter that we usually do on the open source world does like pretty early on is filtering for undesirable content like PII data or like non-safe for work data or anything that is harmful. Like you will try to remove this. Then another very common filter that people usually do is deduplicating your data. That the deduplication could be by document, it could be by line, it could be by paragraph, it could be at different levels. But the idea is to not train too many times on the exact same data. For example, if you train on forums, let's say on all the data that you have on Wikipedia or like Stack Overflow, you will always have these like headers and footers that are duplicated, and you definitely don't want to train like a million times on the exact same Stack Overflow header, because you don't learn much from it. So you would basically be losing compute about to try to learn the header perfectly. Okay, and then you will do some heuristic filtering. You might do some heuristic filtering. For example, you might try to remove low quality documents. Low quality might be that there are too many words. Like if it's an extremely long document, it might be suspicious. If it's a very short one, like let's say there's only 10 words, probably it's not worth training on. If there's many kind of outlier tokens, like tokens or like words that really are extremely rare, it might, it might be that this is just bad data. So you'll do a lot of these heuristic-based filtering. And then you might also do some model-based filtering. So one idea that I find pretty neat that people have been doing is trying to basically do distribution matching. So you find some distribution that you think is high quality. For example, you might say Wikipedia is pretty high quality, or you might say every page that is referenced on Wikipedia is likely to be high quality. Because that means that someone went and referenced that page. So that's already a pretty big amount of data. All the websites that are linked by Wikipedia is pretty large, but it's still very little compared to the amount of data that we need for pre-training. So what you might say is, I want to find more of that type of data. And the way you can do that is that you can train a classifier that takes some random data in and says this is not reference on Wikipedia, and then the pages that are referenced on Wikipedia, and you try to predict basically yes to this and no to the former. And then once you train that classifier, you basically have a classifier that essentially predicts how likely your document is how likely it is that your document is referenced by Wikipedia, and then we can just do a filtering based on that. So you can say if it's very likely, I keep. If it's not likely at all, I will throw it away, because it's probably some bad data. So this is some model-based filtering, and you can do a lot of that. And then you can do some data mix changes. For example, you might like classify the category of data, whether it's like code, books, entertainment, like any of these domains, and then you might want to reweight different domains. So for example, if you train a coding model, you want to reweight coding because probably there's not enough code online. So you want to say, no, even though I only have like 5% of coding, I want to bump it up to like 50%. And the way to do this reweighting, like you can usually do these experiments at small scale. This is true for any of these filtering. You might do these experiments at small scale, try to understand what is best, and then you will try to predict what to do at larger scale. Great, and at the end we'll talk about that too. But once you did all of this like pre-training data, you will also try to collect some higher quality data. For example, you might say like Wikipedia is super high quality, or like everything on like archive might be like really high quality. So you will keep kind of this second distribution of high quality data. And usually after training on this pre-training data, you will do what we call mid-training, which is training on this like high quality data. The idea being like, well, we don't have enough of that data, but we know it's high quality, so we'll optimize. We'll try to kind of fine tune or like optimize after pre-training or continual pre-training our model on that high quality data, such that the model learns to really be as good as possible. Okay, so pre-training data. One paper that I would recommend reading is this Fine Web, and it's both a paper and a blog post about Fine Web datasets from Hugging Face. And they talk a lot about what filtering they've done. But this is just one plot from the paper. And here the x-axis shows the amount of tokens, billion tokens that you train on. So this is still pretty small compared to the scale of pre-training data that we talked about before, which is more than 10 trillion tokens. And this is the aggregated accuracy, where it's like basically your performance on a whole set of evals. And here what they show is first, this green line is when they took 200 trillion tokens from, I believe, Common Core. And then so this is basically raw data. And then they applied a lot of filters. So non-safe for work block list. They mostly went for English text, some simple document filtering. For example, if it's too much repetition in a document, they removed it, or if it's the wrong length. So that's this first filtering went from 200 trillion tokens to 36 trillion tokens. And here we see how well you perform when you train on 360 billion tokens from those. And here you see the performance gain when you deduplicate data. So the way that they've done it is they said, essentially, I don't want to have text that is duplicated more than 100 times. So that's basically at a high level. So they filtered data. They filtered by nearly half, from 36 trillion tokens to 20 trillion tokens. And you see that training on that really improves performance. Again, that's because you're basically not forcing your model to like learn things that are duplicated and like not that useful, and you really focus on new data. So that worked pretty well for them. And I mean, 100 documents, or like 100 documents that are duplicated is still quite a lot, but usually you can have huge clusters of like 100,000 duplicates. So those are the ones that they wanted to filter out. And here you see some additional filtering. So, for example, they removed, I believe, JavaScript. They removed like lorem ipsum text and things like this. So that removed a little bit, again, a little bit more of data, and you see that it performs better. And then some additional, I believe, model-based filtering that performed even better. Great. So that's pre-training data. And then there's mid-training. So as I said before, the idea of mid-training is basically continuing your pre-training to adapt your model to have some desired properties, or to basically adapt your model on some high quality data. So usually you do it on basically less than 10% of what you did for pre-training, so less than a trillion token. So you might, for example, change the data mix in your data. So you might say, I want to have a lot of coding data at the end, or I want to be more scientific and have like a model that is really good at scientific, basically science questions. Or you might want to optimize more multilingual data. Let's say that you know that data is usually, a lot of the data we have access to is more English, but this is not representative of the languages that people usually speak. So you might say, okay, I'm going to upweight some other languages that we usually are less represented in our data sets, just to make sure that it's basically representative of how many people speak that language. Some other type of things we do during mid-training, or that we might want to do, is that you usually want to increase context length. So in many of these models, you usually hear this idea of like how much context can the model see. And when you do pre-training, you don't want to train on very large context lengths because that's much more computationally intensive. But you do want the model to be able to understand, let's say, like 120 tokens that came before your question. So usually what you do during mid-training is that you will bump up this context length. So you will do some extension of context length during mid-training. For DeepSeek v3, they went from 4,000 contexts during pre-training to 128 during mid-training. And I think many other open source projects did that. Other type of data that you might want to add is some formatting or instruction following. So you might want to already teach your model to like answer questions when you ask a question, or to write in a very specific kind of chatty way, and some high quality data. If you have some high quality data, you might keep it for the end and be like, okay, once first I want to learn how to kind of like speak grammatically correctly, and then I want to actually learn the real kind of meat of the text that you have in your data. And you might have some reasoning data, but like teaching the model how to think, which I believe is what Kimi did. And yes. many other things. Great. So pre-training and mid-training, let's just do a recap. One is that really this data during pre-training and mid-training is really a huge part of training LLMs. I would even say that's basically the key for training LLMs. And there's a lot of research that has already been done and a lot more to be done. For example, how do you process well and efficiently? I mean, these are huge scales of data that we're talking about, whether to use synthetic data and whether to use basically models like generate more data, how much multimodal data to put in, how to balance your domains and all of that. And there's a lot of secrecy. So most companies are not talking about what they do. Even in companies that actually do open source models, don't usually talk that much about the data that they collected. First, because it's the most important thing. So there's competitive dynamics, like they don't want to tell you what they've been training on because that would be easier to replicate. And then there's some companies might be scared about copyright liability if they train on data that they shouldn't have trained on. So here are a few common academic data sets. C4, which is C4, the Pile, Dolma, FineWeb. I just wrote a few. So FineWeb is the one we talked about before, 15 trillion tokens. And this is the PAL, the composition of the PAL. And you see that in the PAL there's a lot of archive and like PubMed, high quality data. And you will have also a good amount of like code and things like this. Great. So just to give you a scale of these data, as I said, Llama 2 was trained around like 2 trillion tokens, Llama 3 around 15, Llama 4 between 20 and 40 trillion tokens. So every new generation tries to train on more data and does also some better filtering. Okay, so that was about a pre-training data aspect. Now let's talk about the compute. So in Berkeley, like one thing that's super important is that in Berkeley, for any type of data and model, the most important, as I said before, is how much compute you basically spend on data. On training. So by how much compute, I mean both kind of how much data do you put in the model and the size of the model, because if the model is bigger, you need to spend more compute. And what is very nice is that you can actually predict pretty well the performance, at least during pre-training. You can predict pretty well the performance that you will achieve if you just pour more compute into your run. So if you just train for longer or train bigger models, you can predict pretty well how well they will perform. So here, the way to interpret this plot is that on the x-axis, you see the amount of compute that you have in your run. This is in log scale, and here you have your test loss also in log scale. And all these blue lines are basically different runs. And then you take the minimum achieved for all of these runs, and you can link all of them together, and it gives you something that looks pretty similar, pretty close to a line. And then you can just fit the line to this cover. To discover of the ideal compute and test loss. And now you can use this line to predict how well can you perform if you train on 10 times more data. With 10 times more compute or 100 times more compute. So what is very nice is what I wrote here is that you can now do research at very low scales and then predict how well it will perform at like higher scales. So this is what we call scaling laws, which has which one is very surprising. There's really no good reason for this to happen, or at least, it could have been differently. There are some theories for why that happens. And two, it's really very it's very nice when you do research, because now it means you can work at this small scale and has really been great for the field. Okay, so scaling laws. What is nice, as I said, is that now you can tune things at lower scale. For example, if you have, if I ask you a question and I gave you 10,000 GPUs, I asked you, how should you be using these 10,000 GPUs? How should you be training that model? Like historically, what you might have done is you might like tune high parameters for different models. So you might say, okay, I'm going to have 20 different runs or 30 different runs, and I'm going to pick the best, and that's the one that I'm going to ship. But as a result, each of them will only be trained on like 1/30th of the compute that you had access to. The new pipeline is that now you can find scaling recipes. So you can find like recipes that tell you how to change like the learning rate with different scales and things like this. Then you can tune hyperparameters at small scale for a very short amount of time. And for very, like you can do many, many iterations. And then you can plot the scaling law, extrapolate how well you will be performing at larger scale, and then train one huge model at the end where you use way more of the compute that you have access to. So maybe like 90% of your compute goes for the full run rather than like 1/30th of what you had before. So yeah, this is really a blessing. Okay, so for example, very concretely, should you use an architecture that is a transformer or an LSTM, you see that transformers, this is the scaling law for transformers, and here you see LSTMs. You see that transformers have a better constant, so that means that they are always lower than LSTMs, and they also have a better scaling rate. You see here that LSTM seems to be plateauing a little bit, so that tells you both that at any scale, transformers is better, but also the larger the scale, the better the transformer becomes. Which is why most people gave up on essentially LSTMs as an architecture. But what's interesting is it could also just be that the constant is better for one of the architectures, but the scaling rate is better for the other one. And in that case, you definitely want to always go with the scaling rate, not the constant, because who cares how well it performs at very small scale? The real question is, what if it's like 200 times larger? How does it perform there? And that's why the scaling rate is what matters. Great. So one very famous paper about scaling laws is Chinchilla that tries to explain tries to show what is the optimal way of allocating training resources between the size of the model and the data, because both of these things are about compute, and as we said, the more compute, the better. But you can there are two ways of spending compute. Either you train for longer or you train larger models. So they have these results. I'm going to skip a little bit, but you can basically predict the optimal resource allocation. And they found that for every parameter, you should be using around 20 tokens. So that's kind of this optimal resource allocation. One thing to note, you will hear often about Chinchilla, but Chinchilla is only an optimization of training resources. It doesn't consider inference costs. So they will only ask themselves, they only ask what is the best way to achieve a certain training loss. How much, where should I be putting the compute? But it doesn't take into account that if you have larger models at inference time, they will actually cost more. So for example, if I have, let's say for example, at ChatGPT, at OpenAI for ChatGPT, the larger the model, the more you will spend per user. So you might be better off actually training for longer and training a smaller model, even if it means that you need to spend more compute to achieve the same performance, because at inference time it will cost less. Anyway, so that's the Chinchilla paper. And then I want to talk a little bit about the beta lesson from Sutton. So basically the beta lesson, I would really recommend reading this blog post from Richard Sutton, which is really the big researcher of reinforcement learning. And he wrote that blog post that essentially tries to say the only thing that matters in the long run is about leveraging compute. And the reason why is because we see empirically that the more compute we put in the models, the more improvements you get out of it. So basically, more compute equals better performance. And we also know from Moore's law and some derivative laws that we will always have more compute, or at least that's kind of the hope. We will always have more compute every year. And if you put these two things together, more compute equals better performance, and you will always have more compute, then the natural things that come out of it is that it's all about leveraging computation. There's no reason for trying to optimize things at your current level of compute, because next year you will have more and that will just perform better. So what matters is to have methods that will scale up really well. So that's kind of the TLDR for the beta lesson, which is really has driven a lot of how the community has been thinking in the last, like, I would say 3-4 years. So yeah, so the summary is, don't spend time overcomplicating things, do the simple thing, and make sure that it scales, because what matters, again, is not kind of tuning this constant performance, is really making sure that you can scale it up. Great. So for training a SOTA model, that's this is a slide that I wrote maybe 2 years ago, or 1 or 2 years ago, for training Llama 3 400B, which at the time was the largest open source model. And I just tried to predict like how much that would cost. So in terms of data, I was trained on 15.6 trillion tokens, 405 billion parameters. And you see here that it uses around 40 tokens per parameter. So that's pretty kind of train compute optimal by Chinchilla standards. In terms of flops, it uses 3.8 E25 flops. So there's an executive order that says that you need to basically you need to be more careful when you open source models, or when you train models that are more than 1 E26 flops. So this is around 2 times less than executive order. In terms of flops, in terms of compute, they use 16,000 H100s. And if you do the computation in terms of time, it probably takes around 70 days of training to train this model. And in terms of cost, my rough estimate is that it would cost around like $52 million for training this, or between 50 and like 80 million, depending on how much you consider that they spend per compute given its their own clusters. And in terms of like carbon emitted for training this is around, just for training that one model, maybe 2,000 return tickets from JFK to London, so from New York to London. So that's quite a lot. It's still neglectable compared to I mean, how many flights there are per year and things like this. But if you think that every generation is going to be like maybe 10 times more compute than the previous generation, you could see how in like 2, 3, 4 generations that will become a real issue in terms of carbon emitted. In terms of next model, as I said, it's around basically every generation. You can think about it as like 10 times more flops that go into training the models. Great. Okay, so pre-training summary. The idea is about predicting the next word on the internet. Data, around 10 trillion words go into training these models right now. In terms of time, it takes months. In terms of compute, more than $10 million. The bottleneck is data and computation. And some examples might be DeepSeek V4, DeepSeek V3, and Llama 4. Okay, so now we talked about pre-training. Let's talk about post-training. Again, I'll talk about the method, the data, and compute. So why do you want to do post-training? Well, language modeling, so what we do during pre-training, is really not about assisting users and about helping users. So language modeling is not what you want. And what I might mean by that is that if you just take GPT-3 and you prompt it with explain the moon landing to a 6-year-old in a few sentences, what it will do is that it has been trained on basically a large part of internet. So it will say, oh, well, that reminds me of maybe large lists of questions that people might ask. So instead of answering the question, it might just predict what is a similar type of question that people might ask. So actually what GPT-3 answers to you is explain the theory of gravity to a 6-year-old, explain the theory of relativity to blah, blah. So this really shows you that like these models are really not optimized for predicting what you want. This is just about language modeling, predicting the next word. So the idea of kind of classic post-training, also called instruction following or alignment, is about steering the model to be useful on real-world tasks. So if I explain the moon landing to a 6-year-old in a few sentences, so the same as before, I want ChatGPT or any model to give me a real answer. And the way that we basically do that is to maximize the preferences of humans. So maximize answer preferences of humans. In terms of data, probably around like between 5,000 and 500,000 problems, so much smaller scale than pre-training. The idea is that first you try to basically learn everything in the world, and then you try to optimize on very specific domains, which is in this case kind of just like instruction following and answering questions with very few data points, because the model already knows everything. So it just needs to learn how to basically how to act or how to interact with the human. And this is really what made ChatGPT what it is. So since 2022, that's really when post-training became important. And then, so that's the overview of this like third stage that I told you about, which is the classic post-training. And then there's the second stage, which is about teaching the model to reason. So that only happens in some models. For example, Kimi and R1. The idea is to optimize simply answering the right question, is answering correctly the question. So you will see some, for example, in R1, it says things like thought for 24 seconds. So reasoning is about how do you optimize for that. The data that usually optimized for is basically any hard task with verifiable answers. So things like math competitions or like coding test cases, and you try to optimize for that. So this really became important since 01 in 2024. Yeah, this is about this new paradigm of reasoning. And I believe Noam from OpenAI will also come and tell you about reasoning. But at a very high level, the idea is that what we had before was train time compute. So I mentioned to you scaling laws, which shows that the more compute you pour in the run during training, the better your performance is. And what reasoning gave you is test time compute. So after training, you can also pour more compute in your model to get better performance. And that's kind of like humans. If you make me answer a question in a second, I will probably provide a less thoughtful and less correct answer than if you gave me like a week to answer the question. So the goal was test time scaling. Let me put a bit more light. Great. So post-training methods, I will talk about SFT and reinforcement learning. So the task is alignment. Let's say that you want to optimize, just as an example, let's say that we want to optimize the LLM to follow user instructions or some like designer's desires. So this is the example from before, which is like answering questions, or maybe you want the model to like never answer specific type of questions. For example, if I ask, write a tweet describing how X people are evil, you might want your model not to answer that question. So kind of what I told you before is that the intuition of post-training in general is that you actually know what you want to provide to these models. You do know the type of answers that you want to give, to give to humans. So do know the type of answers that you want to give to humans and what you want your model to like follow. But that behavior, like these answers, are scarce and expensive. So it's pretty expensive and slow to also collect that type of data. But you could just go and try to ask humans what are all the correct answers to every question that you might want to ask. So the idea is that you know what data you know what you want your model to output, but it's expensive to collect that data. But pre-training is something where it's very easy to collect that data. You just take all of internet essentially, but it's not really what you want, as we said. So the idea is that instead, given that one is scalable, but it's not what you want, and the other one is not scalable, but is what you want, what you can do is that you will basically take the pre-trained model that already learned about like grammar and different languages, and you will just fine-tune it or like do some small optimization with data, with the little amount of data that is in the format that you want. And this is what we call post-training. Okay, so there are two methods. The first one is supervised fine-tuning. So the idea is, again, just to fine-tune the LLM with language modeling. So the exact same method as before, but you do it on desired answers. So instead of just predicting the next word, you predict the next word on answers that are the answers that you would want to give to humans. So this language modeling, it means that it's, again, next word prediction, and desired answers is why we say supervised fine-tuning. And so where the S comes from is because you assume that you have access to kind of the correct answer, which is why it's supervised. So how can we collect that data? There are many different ways. One is just to ask humans. This was kind of the key from GPT-3 to ChatGPT, the initial ChatGPT model. And here's some examples from Open Assistant that did that in the open source, where you have a question and then you have answers that are written by humans. You can also do it differently. You can also, one problem basically with human data is that it's slow to collect and it's expensive. So one idea that you might want to do is to use an LLM to scale data collection. This is what we did for alpaca, for example, in early 2023, where we basically said, well, we don't have the money, or we don't have the luxury of having humans that provide us answers. But what we can do is that we can use the best model from OpenAI at the time to predict the right answer, and we can basically try to do supervised fine-tuning with the answer that is given by the OpenAI models. So we did that on 52,000 answers, and we basically, these are some examples, and that kind of, that was one of the first, or probably the first instruction following LLM in the open source. So that really started as kind of trying to replicate ChatGPT. And now this synthetic data generation is a whole field on its own, because the idea is that now actually some of these models are just better than humans. So it's not only that like humans are slow, and it's not only that like human data collection is slow and expensive. It might just be that it's like lower quality. Okay, so let's talk about so for SFT, there's another way of doing it. So we talked about two ways right now. We talked about humans. We talked about LLMs that just provide an answer. But the problem is that if you want an LLM to provide an answer, you kind of assume that you have access to an LLM that is smarter than the LLM that you're training. And that was indeed the case when we were training alpaca. But this is not the case if you're, for example, in the best closed labs, which are training kind of the frontier models, or even if you're in open source and you're trying to train the best open source models, you might not have access to or be able to distill like closed models. So what did DeepSeek R1 do? Because they were training this like first, it's like top open source model. The idea is that you can use rejection sampling based on verifiers. So what I mean by that is that you can just use an LLM to provide many different answers to a question, and then you only keep the answer if it passes if it's correct in some sense. So if it passes some like test case or some verification, or if it's preferred over other answers. So the idea again is, well, you don't have an ideal LLM that you can generate data from and then do SFT to predict that data. What you can do is, if you have access to verifiers or ways of like comparing different samples, if you can roll out many samples, then decide which one is better based on your verifier, and then do SFT on the sample that is given by the verifier. So that's exactly what DeepSeek R1 did for the first stage of reinforcement learning. For the first stage of SFT. Great. So what do we learn during SFT? What are the type of things that we can learn? Well, we already talked about it. We can learn instruction following, so following instructions. You can learn desired formatting or style, like be more chatty, or like use like emojis or things like this. You can use tool use. So I would recommend reading, if you're interested in that, the Community 2 paper or the X-Line paper that basically uses SFT at scale to learn how to use tools. You can learn some early reasoning, so how to think before answering, which is exactly what we just talked about with DeepSeek R1, where they use this rejection sampling algorithm. And honestly, you can kind of learn anything when you have good inputs and output pairs. So SFT can either be seen as a final stage for training a final model or as a preparation for the next stage, which is the reinforcement learning stage. So you don't want to, basically, given that this works pretty well, you might want to do that first before doing the next stage to accelerate the next stage, as we will see. So SFT pipelines can become pretty complex. I'm not going to talk through this one in detail, but I just want to give you a sense of how complicated it can be. This is about Kimi K2, so I would recommend reading that paper and how they use SFT for training for tool use. So basically teaching the model to use tools. And what they did is pretty complicated with some LLM that simulates users, simulates tools, and then do this like rejection sampling that we talked about before. Yeah, so the idea is that they collected a lot of tools. They simulated a lot of synthetic tools that tell you like how the tool should be called, and then they basically have an agent that interacts with an LLM that simulates user and another LLM that simulates tool calls, because otherwise, like tool calls, you might not have access to enough different tools to really simulate like all tools that might be called by the model. And then you basically do some rejection sampling based on these rollouts that were generated with these three LLMs that interact with one another: the agent LLM, the user LLM, and the tool simulating LLM. Anyways, all this to say that these things can become pretty complex, but still work pretty well. Okay, so scalable data for SFT. How much data do you need? SFT, what is nice is that you actually don't need that much data. For learning simple things like style and instruction following, maybe 10,000 is enough. So this is from a paper, a Lima paper in 2023, that basically shows that already with 2,000 examples, you kind of learn the style and instruction following capabilities that you want. If you want to train like more complicated things like tool use and reasoning, you might want to increase that. So I believe R1 used 800,000 samples, which is a good amount, but basically less than 1 million at least. So yeah, the idea is that you don't need to train on much data for SFT if the model already like learned that. So the intuition I usually, like my intuition for these type of things or my mental model is that everything that is already learned really well during pre-training, but you just want to surface during post-training, things like how to write in bullet points or like how to use emojis in your model. This is more about like specializing your model to one particular like type of user that it has already modeled during pre-training. Then for that, you don't need that much data. If it's for things that it has never seen during pre-training or very little, then you need much more data. Okay, so that brings us to reinforcement learning. So the second method, which is RL. So in reinforcement learning, the idea, that the problem that we try to solve with reinforcement learning is that SFT is about behavior cloning of humans or of outputs, as we saw, it could be from LLMs too. But it's about behavior cloning. It's about copying the behavior of different outputs. And this has many issues. One is that it's kind of bound by human abilities or bound by the abilities of the LLMs that you're copying. But humans, even if you're actually collecting human data, they might not prefer the things that they are generating. So even though they might not write like better answers, might not be able to write better answers, they can still say like which one they prefer. So yeah, the idea is that you will always be bound by human abilities. The second thing is that you will actually teach hallucination. And this is a pretty, that's a pretty interesting behavior, is that even if you're cloning correct answers or correct behavior, you might actually be teaching the model to hallucinate if that model did not know that that answer was correct. So what do I mean by that? Imagine that I ask a question to write some introduction, some text, And basically, I ask it to provide some references. If it provides a reference, sorry, if the answer provides a reference that the model does not know about, basically what you're teaching the model is you're teaching the model provide something that seems like a plausible reference, even though that reference, even if that reference was not in your pre-training corpus. So even if you don't know if that exists, still like generate that. So you're basically teaching the model to like make up plausibly sounding references. So yeah, so hallucination, that's one issue. And a third thing is that collecting ideal answers can be pretty expensive. So the idea, or like one solution, is to instead of doing behavior cloning or SFT, you can do reinforcement learning. So instead of cloning the behavior, you can maximize that behavior. So I would really recommend reading the DeepSeek R1 paper and the Kimi K2 papers that are some of the best papers out there in the open source. And the key here is the key in reinforcement learning is to decide like what are you maximizing? What is the reward that you're maximizing? There are different things, for example, that R1 has been optimizing for. One might be rule-based rewards, things like string matches. Let's say that you have close-ended question and answering. You might just say your answer is correct if the answer is exactly X. Or you could have some test cases for coding. So that's rule-based rewards. You can have reward models that were trained to predict human preferences. So we will talk a little bit about that, but you can basically train a classifier to predict whether something is good or bad as predicted by a human and then like optimize against that. Or you might optimize against an LLM-as-a-judge. So using an LLM, let's say you use the best possible LLM and you just say like, what is that answer correct or not? So here, yeah, you see that this particular case which says write a Python code, blah, 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 and then the model generates different answers. And here, given that you say that it's write a Python code, you might have rule-based verification. It says, well, this is not code. Here, this is the answer. Here's a joke about frogs. This is not code. I asked for Python code, so is it Python or not? If it's not Python, then it's also wrong. And then it might check like if you pass some test cases, and it will only keep the ones that are passing. So the idea is to optimize the things that are currently passing. So you just say to the model, do more of the thing that I gave you a correct reward for or positive reward for. Great. So yeah, as I said before, I would recommend reading the DeepSeek R1 paper, but basically they use for reasoning, what they call reasoning prompts, so like math questions, coding questions, and some logical reasoning. They use these rule-based verifiers that we just talked about. And then for general prompts like translation, factual question answering, and writing requests, things that are more like long form text, they basically use a reward model that was trained to predict human preferences, and they try to optimize that. So what they do is that they start with this SFT checkpoint. So they use a model, they do some SFT like this. The model is already pretty good at generating things that are often correct. And then you just do this reinforcement learning pipeline where you try to optimize the number of times that your verifier says you're correct. So in terms of algorithm, the most common algorithm in the open source is GRPO from DeepSeek R1. And the idea is actually pretty simple, is that you take a policy model. So you take your LLM that was usually trained from, there's usually a SFT model. You ask it to answer multiple times to provide multiple outputs to your question. And then let's skip that part for now. You basically have a reward model or verifier that gives a reward, that tells you like, yes, it was correct, no, it was wrong, by how much, and all of this. You get a reward for each. And then you basically do some group computation to get your advantages. The way to just think about it is you do some normalization, just so that you know if which one is very good and which one is very bad. You basically renormalize all of these rewards, and then you basically backpropagate to tell your policy like do more of the thing that was good. And then usually the one we skipped here is this reference model. You usually have a KL divergence, which means that you ask the policy model during training, you say don't move too far from outputs from my base model. And this is really just a hack because you're basically saying reinforcement learning can get you in places that are usually not ideal. For example, the hacks that we talked about. So that's like one way of just saying don't go too far. Optimize as well as you can, but with certain limits of how far you can go. Yeah, and so this is not super important, but basically, if you know a little bit of reinforcement learning, DeepSeek R1 optimizes GRPO, which really just uses the Monte Carlo estimate for computing the advantage, and Kimi-K 1.5 and Kimi-K 2 use a similar loss. Okay, so one thing I want to emphasize is that in reinforcement learning, infra is really key, is really, really important. And the reason why is because, as you saw, if you use this GRPO algorithm, sampling is a key bottleneck because for every input or every question, you have to sample multiple outputs for each of these problems. And especially for agents, given that this is an agent class, this becomes even worse because you might have very long agentic rollouts, and you basically don't want to block all your compute, all your training compute on these very long agentic rollouts that are being rolled out. So Kimi did a lot of optimization, and I would again recommend reading their papers. For example, for long rollouts, Kimi decided to pause these long rollouts. So if it's more than a certain amount of time, it will basically pause the rollout, and it will say, okay, this is not worth it. We will optimize our weights, and then we will resume the rollout the next step. And then another issue with agents is that environment feedback can be slow. So if you have an agent that really interacts with the world and calls a lot of APIs and things like this, like maybe you're not even using your GPUs at all because maybe you're not even like doing rollouts. Maybe you're just waiting for the environment response. So the way that Kimi bypasses that is by using really a lot of concurrent rollouts like this. When a certain rollout is waiting on environment response, you can work on something else. And dedicated services that microservices that can really like spin up and scale. And the way that Kimi did it is that for every pod they have a train engine, then they have a checkpoint engine that broadcasts all the weights to all the other pods, and then they have an inference engine that really does this sampling. And what is important is everything is collocated. All the engines are collocated on the same pod to avoid like communication overhead. So anyways, all this to say that there's a lot of optimization on the infra side, and like infra is really key here. So the communication for them takes less than 30 seconds for communicating the weights, and everything is again working on the same pod. Okay, so let's talk about reinforcement learning from human feedback, which right now we talked about reinforcement learning when you basically, for reasoning, when you have usually ground truth verifiers. The reinforcement learning from human feedback, RLHF, is this notion of reinforcement learning when you don't have ground truth. This is really what made ChatGPT work in 2022. So the idea is, instead of SFT, where you clone the behavior of humans, you want to maximize their preferences. As I said, this is what made ChatGPT, and the pipeline is the following. This is how the original algorithm for ChatGPT worked. You have an instruction that goes to a model, like a question that goes to a model. You ask the model to provide 2 answers. And usually the model is already pretty good. It's an SFT model. And then you ask some labelers to select which of the 2 was better. So you ask some humans, hey, which one of the 2 was better? And then you basically predict, you basically maximize the number of times that you will generate the thing, or you will optimize more. You will tell your model to predict more of this thing that was correct. So there are different algorithms. I'm not going to go through them. PPO and DPO are 2 of them for doing that. But basically, this is just reinforcement learning, where your reward is actually given by a reward model that was trained to classify human preferences. And here you see that these are pretty old results by now, but here you see for learning to summarize, how a pre-trained model performs for summarization. SFT performs better. This is kind of like human reference summary, so how well you compare to humans. And so SFT really improved compared to pre-training, but then you see PPO, so this reinforcement learning made you perform even better. And this is kind of the order of things where it's like pre-training is good, SFT is better, and RL is even better. And same thing here. Those are like this is Alpaca Farm, which is a paper we did for kind of optimizing human preferences. And you see that here that the two algorithms here, those two are two RL algorithms, work similarly, and they work better than SFT, and they work better than the pre-training model. Okay, human data. So as I said, data comes from humans. This is a very expensive, or at least very. It takes a long time to do and pretty expensive too. You have to write extremely detailed rubrics to tell humans what is even considered as a good answer, what is considered as a bad answer. It's actually pretty, a lot of work that goes into collecting data. It's hard. Collecting data is hard. Challenges with human data, as I just said, it's slow and expensive. Second, it's actually hard for really focusing on the content of the answers. Most humans, when you ask them what is good and what is bad, they will usually kind of focus on the form or like the style, things like lengths. And this is usually not what you want to optimize for in your LLM. Also, depending on who you ask, the distribution of annotators, you will really get different behaviors, like different like particle views, and different views on many things. So you have to be pretty mindful about that. There's also crowdsourcing ethics involved here, like who are you asking to label your data? So there's a lot of challenges with human data. Okay, so one way to reduce this dependency on human data is exactly what I told you about before with SFT, is that you can ask an LLM to replace humans to provide preferences. And this is a paper, again, this Alpaca Farm paper that we wrote 2 years ago, which shows on the x-axis the amount of dollars that you need to spend for collecting data, and the y-axis you see the agreement with humans. And you see that actually humans, I believe, are in blue, so are here. So this is around $300 per 1,000 examples that we had to pay humans. And you see that the agreement between different humans is around 66%. While for LLMs, we could divide by 10 or even by 30 the amount of money that we spent. And that was 2 years ago. Right now, it would be way less than that. And we actually performed already better than humans on predicting the correct human answer. So it works surprisingly well. So you can always kind of use this trick of using LLMs instead of humans. But again, this is harder to do when you're at the frontier and you don't have a better LLM. Okay, and then evaluation. So I'll talk really briefly about that, but there's basically two types of evaluation: closed-ended evaluation and open-ended evaluation. One thing to notice, really, evaluation is really the key. It is the most important thing, or one of the most important things in machine learning in general and AI. And the reason why is for three reasons. First, what it does is that it's key to identify improvements, to quantify progress that you're making, and to say whether you're making progress and what to change, what hyperparameters to select, and things like this. The second thing that's really important is that it will allow you to select which model. So which model to use for your application. If I have a specific application in mind, I will have all these different models to train for, to use, to choose from, and I would need to know like which one to go after or to choose. And finally, it's very important to know, evaluation is really important to know whether your model is ready to be put in production. Like, even though your model might be the best current model, like, is it good enough for your application? this is very important. For practical use cases, you really need to have good evaluations of your LLMs. So closed-ended evaluation, the idea is that if you can turn your problem into something where you have a few possible answers, then you can easily automatically verify whether your answer is correct. For example, if you turn your eval into a question answering evaluation, then you can simply ask an LM to provide an answer that is the answer like A, B, or C, and you simply like look at what the right answer was, and then you just consider like your accuracy. So this is, for example, what the MMLU eval did. So there's still many issues. There's still challenges with closed-ended evaluation. One, it's sensitive to prompting, like different ways that you prompt your model will provide different answers. Two, it might have like train test contamination. So if your model was like trained on the eval, because right now, for example, MMLU is all over internet, like maybe your models was like trained on that, it will seem much better than what it actually is. So this is about closed-ended evaluation. I really want to focus on open-ended evaluation because despite these challenges, closed-ended evaluation is much easier than open-ended evaluation. The question for open-ended evaluation is how do we even evaluate something like ChatGPT or like an LLM? So ChatGPT or all these instruction following models, they can be applied on so many different things. So you can be applying it for like coding, for chatting, for summarization, for many things. So you really want to have an eval that kind of covers all these use cases. The second thing is that it's open-ended tasks. So what I mean by that is that you have very like long answers, and as a result, you can't do this accuracy-based evaluation where you just check whether the answer is verbatim like the correct answer. So that makes it hard. So you cannot do this string matching to know whether you're correct. So one idea that you might have for closed-ended evaluation is that you can simply ask humans to tell you whether the answer, like which answer is preferred. So you might show two answers to a human and just ask which of the two is better. So this is what Chatbot Arena by LLM-as-a-judge did, where you basically ask humans to blindly interact with two chatbot and kind of rate which one is better. So that's one way of doing that, of basically dealing with this challenge where when you ask open-ended tasks with like where there's not a single answer and the answers are usually really long, it's easier. Yeah, it's much easier to just ask humans to kind of rank things than to compare to a gold answer because there's no gold answer. The problem with this is that using humans is again kind of costly and expensive. Expensive and slow. So just as before, what you can do is you can use an LLM instead of a human. This is what we did with Alpaca eval 2 years ago, and many others followed. The idea here, the steps, is that for each instruction, for each question, you might ask a baseline that could be a human or a model to provide an answer, and the model that you try to evaluate to provide an answer. And then you will just ask another LLM which of the two answers is better. And then you will just kind of look at the number of times that your answer is better than the baseline. And you can get what we call a win rate, which is the probability of winning. So Alpaca eval was kind of one of the first eval doing that. And despite being much cheaper than Chatbot Arena, it had really high correlation, Spearman correlation with Chatbot Arena. So using LLMs can be really good as like as a judge for judging your performance and for evaluating your performance. Yeah, so it costed, like running Alpaca eval right now probably costs much less, but at the time was less than 3 minutes and less than $10. Great. Okay, so I think I'm getting at the end. I do want to tell you a little bit about systems and infra, because as I said, if you really understand kind of the fact that scaling is what matters, then the natural question, the natural thing that you should be spending time on is also like making sure that your models, your training can scale well. So the problem is that everyone is bottlenecked by compute. So one idea that you might have is like, well, if you're bottlenecked by compute and if you know that spending more compute gives you a better answer, why just not buy more GPUs and training on that? There are a few reasons why we can do that. One, of course, GPUs are expensive, but they're not only expensive, they are scarce. So even if you have the money, it can be hard to just get access to the best GPUs. And then there are physical limitations. So if you have a lot of GPUs, you need to have the communication between GPUs, and that can really slow down your training. So you do need to kind of optimize your systems and make sure that like training is as efficient as possible on every GPU that you have. So yeah, you need to do some good resource allocation, and you need to optimize your pipelines. Okay, so I will try to give you an extremely brief overview of GPUs just for you to get a sense of what matters when you optimize these runs and what you're actually optimizing for. So Systems 101 GPUs. So the difference between GPUs and CPUs is that essentially GPUs are massively parallel. So they will apply the same instructions in parallel on all different threads, but different inputs. So you will have the same input that will go on different threads, and it will basically different inputs that will go through different threads and will apply the same instructions to them. So really, the difference with CPUs is that you're optimizing for throughput. It's massively parallel. So here you see GPUs and CPUs, the difference. So yeah, as I said, first, GPUs are massively parallel. Second thing is that GPUs are really optimized for matrix multiplications. So GPUs are graphical processing units and graphical, anything about computer vision and graphics really requires extremely fast matrix multiplications. So from kind of the early days of GPUs, people were really optimizing, or like the GPU, people building GPUs are really optimizing for matrix multiplication. So they have specific cores that will make matrix multiplication very fast, and actually around 10 times faster than most other floating point operations. So here you see different versions of GPUs, and you see kind of the speed, and you see that for matrix multiplication is much faster, especially recently, much faster than non-matrix multiplication floating point operations. So another thing that is important to understand about GPUs is that actually compute is not the bottleneck anymore. So what I mean by that is that if you look at here, kind of the compute that like the peak hardware scaling. So here you have computes of flops that could be performed on the best hardware across time, and here you have basically the communication and memory and how it improved across time. And you see that basically compute increased or improved much faster, across time than memory and communication. So what that means is that right now we have more compute in a GPU than we have like memory, and then we have improvements in communication. So in other words, what the bottleneck for GPUs is not performing the computation, but it's actually keeping the processor that performs the computation fed up with data. So you basically need to send as much data as possible there, and it's the bottleneck is actually feeding the data, not doing the computation. That's a very important thing to understand when you're optimizing your pipelines. As a result, if you look at this paper for like 2020 that analyzes where you perform all the compute for how much time it takes to run a transformer, you will actually see that things like tensor contraction, which is basically matrix multiplication, requires most of the flops. So most of the actual compute that is required is for matrix multiplication. But in terms of runtime speed, This is actually pretty, it's still a majority, but it's only 2/3 of the runtime is spent on the thing that is most of the compute. And things like element-wise operation, or like some normalization, actually requires very little floating point operations, but requires a pretty large amount of time, or basically you spend a lot of time there because you need to still like send to the GPUs your data and do the computation, even if the computation is slow. Okay, and last thing that you need to know about GPUs is that there's really a large memory kind of hierarchy. So the closer you are to the cores being the things that actually perform the computation, the faster the faster the communication with the cores will be, but the less memory there will be there. And the further you're from the cores, the more memory, but the slower. And you basically have like different levels of hierarchy. So you have this shared memory, and then the L1 cache that is the shared memory that is super close, and then you have the L1 cache, the L2 cache, and then you have the global memory that is very far from your registers and your your process. So this memory hierarchy, and the metric that we try to optimize when we try to optimize our runs and just our systems is model flop utilization. You will often hear this word, or MFU for short, and this is basically the ratio between the observed throughput to your model and kind of the theoretical best. So like NVIDIA will tell you, at best, we can do that amount of flops, and then you will check like how much you are achieving. And if you achieve MFU of 1, that means you are able to get all the data, the maximum of data. You can always keep your processor basically fed with data. So at any point of time, there's something that is being computed on your processor. Just to give you a rough sense of these numbers, if you have 50%, you're in a really, really, really good shape. And even big companies might be optimizing to go like higher than 15 or 20% and to achieve like this 50%. Great. So I want to give you a very quick overview of like things that you might want to do for optimizing your runs. Just to give you a sense of like, at least like things that people do for optimizing kind of this compute and making sure that your runs are scalable. One thing that you might do is low precision compute operations. So the idea is that if you use fewer bits for every data points, or for every data that goes in your processor, you will have faster communication and low memory consumption. So as I said, given that the bottleneck is not the compute, but it's kind of this memory and this communication, you might just decrease the precision in which you put your data in, and as a result, you will just have faster communication because you can put more through the bottleneck and lower memory consumption. So, for example, for deep learning, the actual kind of decimal precision is not that important, except for a few operations. That's because there's a lot of noise in any case, when you train deep neural networks, because of stochastic gradient descent already has a lot of noise. So matrix multiplications will usually be done in BF16 rather than FP32, so you can halve the precision. And if you halve the precision, what you can do, so usually like one thing that is very common is using automatic mixed precision, or AMP, during training, which is that the weights are stored in FP32, so you use 32 bytes. But before you compute, before the computation, you will convert the FP32 to BF16. So you will basically half the precision, and then everything will be done in BF16. So you will have less memory, you will have more speed up because faster communication, and your gradients will be stored in BF16. So you'll have memory gains, and then at the end, you will put it back in FP32, and like this, every like small operation that you do can be shown in your weights at pretty high precision. Great. There are other optimization, for example, operation fusion. So again, the idea here is that communication is slow, as we said. And every time that you, for example, if you write in PyTorch, every time you write a new line, it actually moves your variable back to global memory. And that makes it very costly because basically if you do something like x1 is equal to x, the cosine of x, you will basically read from x, read x from global memory, write it to x1, and then when you do this new line, x2 is equal x1 cosine of x1, you will again take it back to global memory and write it to x2. So that can be really very slow because you have a lot of this communication between global and memory. And so what you might want to do, so this is just to give you a schematic version of what is happening. So here you have everything in memory, your DRAM, and basically you will send data to your processors for performing compute. And after every new line, you will send it back to your DRAM, and then you have to do it again and do it again. So this is kind of a naive way. If you just have a PyTorch function, this is a naive way that things are working. But there's a much better way of doing that once you realize that communication is the bottleneck, is that you might just communicate once and do all the operations and then communicate it back. So this is what fuse kernels are doing. So the idea is that you communicate once, you perform all the operations that you want, and then you send it back. And as we said, this is actually fast, this is slow, so there are fewer slow things here. And this is basically what torch compile does to your code, is that it kind of fuses operations together. Okay, tiling. I know it's becoming long, so I'll just quickly talk through that. The idea is that the order in which you perform operation will matter a lot because of communication. So what I mean by that is that you can group and order threads that are performing some computation to minimize the number of times that you will communicate with global memory. So I'll give you an example for matrix multiplication. Here, this is the very naive way of doing matrix multiplication, where this is how you basically learned it at school, where you take two matrices that you multiply them, you will basically go through all this column and all this row, you will basically multiply these two together and multiply these numbers and then sum across all of that, and you get this number for this one. And the way that basically the memory is accessed here is that one thread here is going to access this one and this one and then this one and this one, and you'll basically have one thread that is working with all of this and then all of this one, and then you will have another thread that is working on these things separately, and then this one is done, it will work on a different column and a different row. So what is important here is that you will rarely reread the same values from cache. In contrast, what you can do is you can split up your matrix multiplication into different tiles to reuse memory. So for example, you might say, well, I'm going to have one thread that instead of working with all the column and all the row at once, it basically works with all of these four values together against these four values together. So you basically do multiply this and this together, and then this one and this one together. And then basically once you're this one, sorry, it's a bit hard to explain without actually showing it to you and just with this diagram, but basically this number here, n00, will be used twice, will be used to multiply m00 and m10. So basically, for one number that I have access to, I made two operations. So I have n00, I made two operations. So basically, I have to read less from global memory because by one read, I made two operations. While before, with one read, I made only one operation. So you're basically making sure that you make more work with the same amount of data or more, sorry. or same amount of work with less data. So you basically read less. And you can still work through an algorithm like this where you multiply these element-wise with this, and then you have another thread that works with this one, element-wise with this one, and then you have the partial sums and you sum them together. Anyways, all this to say, it's not super important. The actual kind of algorithm is really not that important. What is important is that the order in which you perform operations can really impact, or like the grouping and ordering can really impact the number of times that you have to read from global memory. And tiling is one way where you basically group things together in a single thread, such that with less data, you can do more computation. So you can kind of reuse reuse the reads and basically have access to your cache. Great. So flash attention is one pretty famous optimization that was done for making attention faster. And it basically kind of combined the three things that we talked about before, which is this kernel fusion, this tiling, and also one additional thing, which is recomputation. So sometimes actually it's cheaper. Sometimes it's cheaper to redo a computation than actually reading from your memory the values. So basically here the recomputation of attention is the idea that like don't save everything. Sometimes it's easier to just recompute the values than like storing them. And flash attention v1 got 1.7 end-to-end speed up from tree. 1.7x speed up gains just by combining these things together. So all this to say that systems really matters. You can get huge speed up gains at no ML. This is a completely ML neutral. This is just kind of an order of operation. The order in which you perform operation can really improve a lot your performance. Okay. I think I'm arriving at the end. I do want to maybe briefly talk about parallelization. That's kind of the last big topic in terms of systems. So the idea is that you have very big model. This is one of the big problems, that you have very big models, and big models cannot fit on one GPU. So you really want to use as many GPUs as possible for making your training runs fast. So once you think about it this way, there's a question of like, how do you split your GPUs? How do you work with as many GPUs as possible? And how do you fit your model into GPUs? And the idea is that you can split your memory and your computation across GPUs. So again, kind of the problem is that models are big, they don't fit across GPUs, they don't fit on a single GPU. Two, you want results as fast as possible, so you want to put as many GPUs as possible working together. And the idea is that you can kind of split the computation and split the memory across different GPUs. And this is all about parallelization. Okay, slight background here is to naively train a model that has P parameters, you actually need 16 times P gigabytes of DRAM. So the reason is that you need 4P, so 4 bytes, because here we assume that it's 32 floating, like, yeah, FP32. So you have 4 bytes for every P parameter. And so you have 4P gigabytes for model weights. Then for the optimizer, if you talk about Adam, you need to store both the mean and the variance of every parameter. So the optimizer needs to store 2 times 4P gigabytes in terms of values. And so you have here 12, and here you have 4P for the gradients. So you need to store both the forward, both the weights, and when you do backpropagation, you need to store the gradients, and this is also 4P. So basically that means that for training a 7 billion parameter model, you actually need 112 gigabytes of memory, which is really huge. So the idea here is that you can optimize that by the goal at least is to use more GPUs and to optimize your training. So let's say that you have 4 GPUs here, and you want to optimize. You want to basically have every GPU working simultaneously on your data set. One naive way that you can do it is that you can copy the model and the optimizer on every GPU. You can split the data, and then you can basically have every GPU working on a different on the same model but different set of data, because you split up your data. And then at the end, after they do one step, you basically communicate the gradients and sum the gradients, and that will be the total gradient that you would have gotten if you had actually trained on the 4 sets of data. So basically, after every batch, everyone works on a separate batch, and then at the end you get gradients. You communicate, you sum them, and then you have basically the same gradient as what you would have had you trained on 4 times the batch size. So the benefit is that now you can use all these GPUs because now you can use 4 times more GPUs than before. So it's 4 times faster than before. The negative aspect is that here you have literally no memory gains, because now if your model, for example, didn't fit on 1 GPU, it still doesn't fit on a single GPU right now. And also here we said 7B models require like 112 gigabytes of memory. Here it means that you really need to have 112 gigabytes of memory on every GPUs. So there's no memory gains. So how would you split memory? How would you get memory gains? One way of doing that is to have each GPU update a subset of weights. Update a subset of weights and hold the subset of weights, and then you communicate them before updating your weights. So this is what we call sharding. So here this is one way of doing that is this paper called Zero. So here you see the baseline, which has the 4P parameter, 4P gigabytes for parameters. Here you have the 4P gigabytes for gradients, and here you have the 8P gigabytes for optimizer states. And they have different levels of sharding. So you can shard, the first thing that you can shard is you can shard the optimizer. So you can say, well, every GPU will only have one subset of optimizer states. And basically, each of them contain a subset, and we'll just like communicate them when needed. So you basically have this, and then you can do the same thing. So this will cut a lot your memory requirement from 120 gigabytes to 31 gigabytes, so nearly a 4x decrease. And then you can do the same thing for your gradients, and you can do the same thing for your parameters. So you can basically say every GPU takes care of a different subset of weights. Okay, so that was for data parallelism. Now let's talk about model parallelism. The problem with data parallelism is that it requires your data to have at least as much data as you have, or at least as much batch size as you have GPUs. So basically, as I said, is assume you have a batch size of 16. Basically, what you're saying is if you have 4 GPUs, you have 4. Every GPU now gets a batch size of 4, so 16 divided by 4. But what if I want to use 32 GPUs? Like, how do I now split up that data to fit into 32 GPUs? The idea is that you can have every GPU take care of applying specific parameters rather than updating. So what we saw before with this data parallelism is that every GPU can take care of updating specific parameters. But here the idea is with model parallelism is that instead of having every GPU taking care of updating the parameters, you can have every GPU taking care of applying the parameters. So like applying the actual operations. So, for example, in pipeline parallelism, you can say that every GPU has access to holds different layers. So you can say layer one is on GPU one, layer two is on GPU two, and basically what you have is that once you predict, once you take data, you make all the data pass through your first layer, which is on GPU one, and then you send it to GPU two. It passes through the second layer, and GPU three, etc. So this is for pipeline parallel. I'm gonna skip that part, and then you have tensor parallel. So this is the idea that instead of splitting, instead of having every GPU hold a different layer, you could have you can kind of split matrices, or you can split inside of a layer. You can split between GPUs. So for example, when you multiply two matrices, when you multiply a matrix with a vector, what you can do is you can split up the matrix into two, you can split up the vector into two, and you can basically say, I'm going to operate with these matrices on this vector, and let's meet these matrices on this vector, and then I'm going to aggregate everything at the end together. So this is what we call tensor parallelism. So pipeline parallelism is this idea that every GPU has different layers. Tensor parallelism will basically split up the weights into different GPUs. Great. Okay, and the last example for system optimization is that models are really huge. So instead of kind of splitting up your model onto model weights onto different GPUs, what you can have is you can say, well, actually, not every data point has to go through every parameter, and this is what we call sparsity. So very common architecture that is sparse is the mixture of experts that basically says only some parameter will be active for some types of data sets, sometimes of data points. So the idea is that you now have a data point that comes in, and it will only go to some set of parameters, not all the parameters. And this makes it very easy for doing for doing parallelism and like multi-GPU training, because you can just have different GPUs contain the parameters that are required for different data points. So here you have a dense model that basically, this is a kind of insight, a little bit too much maybe into the weeds, but if you know about transformers, you have this like linear layer at some point, and you can basically say the linear layer is going to be split into like different linear layers, and different data points will go through different linear layers, and every GPU can basically have access to different linear layers. So if you didn't follow kind of the last two slides, though, maybe a little bit not as important, but what I do want to stress is that there's a lot of work that goes into systems optimization and the kind of optimizing the use of your compute. And the different ways that we saw about doing that was tiling, so like ordering of your operations. It was the sparsity, so basically making your model sparse and not having every data point go through every parameter. We talked about parallelism, so basically using more GPUs. Yes, I think that's basically it. Great. So we're done. There's no questions today because, as I said, this is a re-recording of the video. I know this was pretty long. I'm also starting to be a little bit tired, but I hope it was useful. And yeah, good luck for the rest of the class.